Hello, ladies and gentlemen, and welcome back to this question number 4 on the 2017 Friar Contest. That is the grade 9 written contest. So, we're going to be doing question number 4, and it is the very last question. I'm going to finish up the whole paper now. Let's have a look. Hopefully you've already had a look, and you're just coming here to confirm answers or brush up on your written question technique. So, question 4 starts with quite a bit of a preamble. 3 students sit around a table. Each student has some number of candies. They share their candies using the following procedure. Each student with an odd number of candies discards 1 candy. Oh dear. Students with an even number of candies do nothing. So that's step 1. Step 2. Each student passes half of the candies they had after step 1 clockwise to the person beside them. Steps 1 and 2 are repeated until each of the 3 students has an equal number of candies. The procedure then ends. On Monday, Dave, Yana, and Tam start with 3, 7, and 10 candies respectively. After step 1 and 2, the number of candies that each student has is given in the following table. So what would Dave do? Dave has an odd number, so he would discard 1 and get down to 2. Yana has an odd number, so she would discard 1 and get down to 6. Tam does nothing because Tam has an even number of candies. Then Tam takes half and passes so 5 go to Dave. And you say, well, 2 plus 5 isn't 6. Yeah, but half of Dave's, which is 1, gets passed to Yana. So with the 1 that's left over plus the 5 from Tam does make 6. 1 from Dave, and then half of 6 is 3, makes 4. And then the other half, the other 3 from Yana, get passed to Tam. 5 plus 3 is 8. Okay, so there's a lot going on there, but we can carefully walk ourselves through this. Alright, we got 4 parts here, 2 light bulbs, 2 writtens. I would guess the light bulb questions are worth 1, maybe 2, and the written questions are worth sort of 3, maybe 4 marks. So we keep that in mind when we're writing things up. Don't write excessively for something that might only be worth 2 marks. Okay, time is a factor on these contests. We only get 75 minutes. 8 part. When the procedure in the example above is completed, how many candies does each student have when the procedure ends? I bet it will end after 1 more step, because I don't think they're going to make this too hard on us. Alright, so let's work our way through this. So we know Dave, Yana, and Tam. So Dave's got 6, Yana's got 4, Tam's got 8. So after step 1, well, they both have the same amount of stuff. After step 2, and I'm just going to keep track, so this gets split into 3. 3 goes here, 2 and 4. So 2 gets sent here, and 4 sort of wraps around and goes down here. 4 plus 3, Dave gets 7. 3 plus 2, Yana gets 5. 2 plus 4, Tam gets 6. Okay. So step 1, Dave discards 1, 6. Yana discards 1, that's 4. And Tam continues to have 6. Step 2, so I'll go back to color. So Dave's 6 gets split up into 3. Yana's gets split up into 2. Tam's gets split up into 3. So Tam passes 3 to Dave, who still has 3 left, gets 6. Dave passes 3 of his 6 to Yana, and Yana still has 2 because she split the pile. So 3 plus 2 is 5, and 2 and 3 give Tam 5. Alright, the numbers are slowly getting closer together. Step 1 again, nothing happens to Dave. Yana and Tam both go down to 4 candies. And step 2 here. Notice that eventually we'll eventually get down to, I think, 0 no matter what, because we're always decreasing the total number of candies. If either the total number of candies remains constant or it decreases, it never increases. So when we began this question, we had a total of 18 candies. Now we're down to only 14 candies. So 3, 2, 2. 2 plus 3 is 5. 2 plus 3 is 5. 2 plus 2 is 4. Now we're down to, well, we still got 14 candies. So it doesn't change between step 1 and 2. 4, 4, and 4. Aha, suddenly we're done, and it won't change after this step because it's going to go 2, 2, and 2. And 2 plus 2 is 4, 2 plus 2 is 4, 2 plus 2 is 4. So there we go. Oh, sorry, step 2. So that took a lot longer than I thought it would. I guess it is question 4. So what were they specifically asking for? How many candies does each student have when the procedure ends? It's light bulb, although we did show our work. So we'd say something like each student has 4. Okay. Very simple, very basic algorithmic question. If you understand the process, I'm sure we can keep doing things. We've also noted some things. I just like to write them down, possibly for our written stuff later. So the number of candies in total never increases. And another thing, during step 2, the number total of candies stays the same. I bet that's not going to be a particularly helpful observation. The first one might be, second one, not so much. Because I think we're probably going to be treating steps 1 and 2 together as a process, because we do step 1 and 2, then we say, do they have the same number of candies? Do step 1 and 2, then they have the same number of candies, that sort of thing. We could probably make a third observation that if at step 1 they have the same number of candies, at step 2 they'll have the same number of candies, but doesn't really matter. Okay. B part. On Tuesday, oh yeah, they did say on Monday. Nice. On Tuesday, Dave starts with 16 candies. Each of Yana and Tam starts with 0 candies. How many candies does each student have when the procedure ends? Okay. So we're given just some different starting information, but the same process is going to apply. Dave, Yana, Tam, 16, 0, and 0. Alright, so step 1, well, nothing's going to happen because they all have an even number of candies. Step 2, Dave gets 8 plus half of 0, Yana gets 8 plus half of 0, and Tam gets half of 0 plus half of 0. Step 1, nothing happens. And step 2, half of 8 plus half of 8 is 8. Half of 8 plus half of 0 is 4, and then half of 0 plus half of 8 is 4 again. Alright, step 1. By the way, notice that they're not going to be able to split these 16 candies equally amongst themselves. You would never get, C, 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 and have that total be 16. It'd have to be 3 C candies in total. So we're going to be dropping some candies at some point. Now, we haven't hit any odd numbers yet. Odd numbers are the only times we lose candies. So we just sort of keep these things in mind. Step 1, nothing happens because they're all even. Step 2, half of 4 is 2 plus half of 8 is 6. Half of 8 plus half of 4 is another 6. Half of 4 plus half of 4 is 4. I would like to observe that here these two have the same, then here these two have the same, then here these two have the same, and now these two have the same, because nothing's going to change with 6, 6, and 4 for step 1. And step 2, half of 4 is 2 plus half of 6, we get 5. Half of the 6's is 6, and then we get another 5 here. There are the odd numbers. So for step 1, we remove and round down 4, 4, and 6. And now I have a total of 14 candies. Well, that's still not going to be enough to spread evenly. But these halves go to 4. half of 4 and half of 6 is 5. Half of 6 and half of 4 is 5 as well. And this should round down nicely. 4, 4, 4. And after step 2, once again, 4, 4, 4. So it's interesting to note that we have 12 candies. We started with 16. We skipped right over 15. I don't think you can ever have an odd number of candies be the total when they're all even. I mean, I could be wrong, but I don't think that'll ever happen. So it looks like the answer should be the next greatest multiple. The next greatest multiple of 6 after what you start with. Just a guess, but we're done the light bulb, so we can say they all end with 4 candies. And that is what we were asked for. How many candies does each student have when the procedure ends? All right. C and D. On Wednesday, the next day, Dave starts with 2 N candies. Each of Yana and Tam start with 2N plus 3 candies. Determine with justification the number of candies in terms of N that each student has when the procedure ends. Okay. So 2N plus 3, 2N plus 3. So the total number of candies here is going to be 6N plus 6, which I think it'll be the same number of candies. So I think that everyone will get 2N plus 1 at the end. Just a guess, but based on what I've seen, I feel like the total number of candies at the end should be a multiple of 6. And we've already got a multiple of 6. So here's where we would definitely need to be showing our step 1s and things like that. We've been doing it for A and B, but for the written question, we got to justify what we're doing. So 2N, 2N plus 3, 2N plus 3. Now immediately, we have to note, these are odd. Okay, so now it goes down to 2N, 2N plus 2, 2N plus 2. So step 2, have the number of candies, pass them over. So this is going to be 2N plus 1, this is going to be 2N plus 2, and this is also going to be 2N plus 1. I don't think we need to talk about the algebra every time we do this. But I do think we need to note, these are odd. These ones here, also odd. You should be noting when they're odd, because that's when step 1 actually kicks in. So that'll go down to 2N and 2N. We get 2N plus 2. Step 2, so this goes to 2N. This becomes 2N plus 1. This becomes 2N plus 1. And once again, we have some odd numbers. And that's when step 1 kicks in. So we'll get 2N, 2N, 2N. And with step 2, we get 2N, 2N, 2N. Now I feel like that's kind of light. So maybe off on the side you say, 1 half of 2N is N plus 1 half. But I think that's a lot of work. I think we're fine here as long as we note when things are odd. So I might also say something like after 3 of the processes, or 3 applications of the algorithm, Dave, Yana, and Tam have 2N candies each. Now, I think I was going to say that this applies to situation in B, but no, they started with 2N, 0, and 0. So, no, I think we're good. We noted when things were odd, and that's when step 1 kicked in, and we have our final answer. So I think that's fine. That's fine for C. And then we got D part here, which I believe I did see 2 to the 2017. So on Thursday, Dave starts with 2 to the 2017. Obviously, this is a math question because no one would ever have that many candies. I mean, I'm pretty sure that number of candies would fill up more than the solar system, just because that is a ridiculously huge number. Okay? But the point is, it is a ridiculously huge number. We're not going to be able to write it out, and we're going to have to rely on, it's a power of 2, so it's even, that sort of thing. So once again, I've seen we got a power of 2, just like we did in B part. 16 is 2 to the 4. So D seems to very much be a gross exaggeration of B part. Because we've got Dave starting with a power of 2 number of candies, each of Yana and Tam starting with 0 candies. Determine with justification the number of candies that each student has when the procedure ends. Okay. I'm going to start off like I did in A, B, and C and just carry everything through and make a chart. And I think the chart should do fine for me. Okay. What did we see before? It was 4, 4, and 4. So maybe 2 to the 2015 is what everyone will have collectively. That's my prediction. In fact, if we wanted to, we could be really super general about this and say, 2 to the n. I think I'll do that just for fun. So step 1, well, all of these are even. And you could, if you wanted to, you could say, well, they're all even. That's your justification for that step. Step 2, this will split up and we'll be left with 2 to the n minus 1, 2 to the n minus 1, and 0. Step 1, well, they're all even. So same numbers here. Step 2, this one stays the same, and these become 2 to the n minus 2. Alright, step 1, well, as long as n is greater than 2, which in the particular case where n is 2017, this is true, these all stay the way they are. Step 2, see, this will stay 2 to the n minus 2. This will be 2 to the n minus 2 times, okay, so half of 2 to the n minus 1 is 2 to the n minus 2. Half of 2 to the n minus 2 is 2 to the n minus 3. I'm going to take out the factor of 2 to the n minus 3 and say it's 2 to the n minus 3 times 2 plus 1, which is 3. And this one will also add 3 to the 2n minus 3. Okay. So that's interesting that we introduced the 3 there, and that happened before with those 6s and everything. But it's still even, as long as n is greater than 3. So we'll still have 2 to the n minus 2, 3, 2 to the n minus 3, 3, 2 to the n minus 3. Once again, I'd like to remind you, I'm keeping the n in there just as a fun little challenge. So that if they then ask me about 2 to the, Dave getting 2 to the 4 billion or something like that, I'd be able to answer the question. Okay, now it's getting a little harder. So now is when you'd probably include side calculations at this point. So that's side calculation for this one. Side calculation for this one, 2 to the, this is always going to be 3 to the 2, 3 times 2 to the n minus 3, because it's the same number repeated here. So half of this plus half of this gives you the same number. But now half of 2 to the n minus 2 is 2 to the n minus 3. Half of this is 3, 2 to the n minus 4, which is going to be 2 to the n minus 4, and then 2 plus 3, which is 5. So 5 times 2 to the n minus 4, 5 times 2 to the n minus 4. Now, we're getting similar numbers to what we had before. So this is analogous to 5, 5, and 6. But if we recall in B, things didn't, the total number of candies has not changed here. So this is where we would need to say something like, the total number of candies needs to be a multiple of 6. And this is also, the only way we got from 16 down to 12 was when we were odd and we rounded down. Okay. So I think the total number of candies isn't going to change until everything becomes odd, and we round down. Okay, so when is that going to happen? Well, we need to start talking about things like, so I notice right now we've got something n to the 4. Or sorry, to add 2 to the n minus 4, and 2 to the n minus 4, and 2 to the n minus 3. Well, if n were 4, we'd have 5, 5, and 6, and we'd be rounding down, like we did in B. But in this case, n is 2017. Big number. What are we to do? Well, we're going to have to keep repeating this process. Okay? And the numbers are going to be more and more and more spread out. Yeah. The question is it ever going to sort of cycle around and come? I don't think it will. Because it looks like we had 1 times, and then 1 plus 2, 3, and then we got to 4. I think the next time it should be 7. So I'm just going to carry over for 2 or 3 more steps, just so I can better understand this pattern. But I think we're going to actually have to argue something and not just write out a chart 2017 times. So, we can't round down yet because they're all still even. 5, 5, 3. Okay, yes. But now the interesting thing is what happens with step 2. Okay, because I'm imagining in the future we have an odd number times 2 to the x and an odd number times 2 to the x, or something like that. Alright, so a half would be this, plus, so this one will stay 5 times 2 to the n minus 4. And this will be, so half of that is 3 times 2 to the n minus 4. Take out the 2 to the n minus 5, and we're left with 5 plus 3 times 2, which is 11 times 2 to the n minus 5. Okay, now that's interesting, because I thought we might get 7. We didn't. So what is sort of the recursion? What's going on here? So I'm getting close to an argument that I want to make. So we're going to get 11 times 2 to the n minus 5, 11 times 2 to the n minus 5. And then what happens after that? So right now our pattern is 1, 3, 5, 11. And it looks like after the 1 and the 3, I guess technically it would be 0. But I'm not going to count that. So from 1 to 3 we get to 5 because that's 3 plus 2 times 1. And then from 11 we get 5 plus 2 times 3. So the next one we should get 11 plus 2 times 5, 21. That's my prediction. So step 1, nothing to round down again, assuming n is big enough. Okay, eventually, once we get down to a case where it looks like 2 to the n minus 2017, then we'll have something to do. But we don't currently have anything to do with step 1. Step 2, this one stays the same because he's the second one. And then we have 5 times a half of that plus 11 times a half of that. I added 1 when I shouldn't. It should be minus 6. And then this leaves me with 5 times 2 plus 11 times 2 to the n minus 6. So that's where it's coming from. Okay. Is there a general formula for these numbers? multiply by 2, and so we get sort of these ANs, and AN plus 1 is you multiply the previous one by 2 and subtract 1 to get 21, but I would add 1 to get 11, subtract 1 to get 5. So definitely a pattern going on here. Okay, so 1, 3, 5. So this is our first term, second term, third term, fourth term, I think. So this is A1, A2, A3, A4, A5 is 21. So AN plus 1 is equal to 2AN plus negative 1 to the n plus 1. So to get A6, I would do twice 21, which is 42, and then I would do plus 1, 43. And that makes sense because 2 times 11 is 22, plus 21 is 43. Okay. I just want to prove this formula for a second. So assuming it is true, you get something like this. But then that's 2. So, but this is AN minus, yeah, so this part here is AN minus n minus 1 to the n plus AN, so that'd be 2AN plus negative 1 to the n plus 1, because this minus becomes the plus 1. All right, so yes, that formula works. Okay, so here's my plan. If we start with AN 2 to the 2017 minus n, AN 2 to the 2017 minus n, AN minus 1, 2 to the 2017 minus n plus 1. Step 1, I know what I want to do, I'm just having organizational troubles in my head right now. Okay, so, 5 is actually with n minus 4. So maybe we should call this 0, 1. No, we should go up a level. 2, 3, 4, 5. And so that should be AN minus n plus 1. Right? No, I think it should still be plus. So that'd be 5 times 2 plus, no, it should be minus, yeah. Shifted the sequence down a bit. Okay. Alright, so if we start with this, all the ANs are odd, which I think is probably also something that should be proven at some point. But then we get AN 2 to the 2017 minus n, and 2 to the 2017 minus n. an minus 1, 2 to the 2017 minus 2 plus 1. And here we are assuming n does not equal 2017. Then step 2, we would, this one stays where he is. But then this becomes an plus 2, an minus 1, 2 to the 2017 minus n minus 1. So we go a step further, and this one also. an plus 2, an minus 1, 2 to the 2017 minus n minus 1. Okay, and we could show this, but I've already done a couple examples of this. Which is equal to an plus 1, 2 to the 2017 minus n plus 1. an 2 to the 2017 minus n, and an plus 1, 2 to the 2017 minus n plus 1. This seems kind of long for a Friar 4, so I feel like I've missed an obvious way to do the question. But it is written, and we do need to justify these sorts of things. So all the ANs are odd. I think that's pretty clear, because we double an odd number and then add on another odd number, so it's even plus odd. They're all going to be odd. But if you wanted to, you could justify. That would probably need some justification. This pattern, pretty clear that it's repeating. What do we want to say now? The pattern repeats until n is equal to 2017. Because here, assuming that n is not equal to 2017, all of these are even, so step 1 does nothing. Now what happens when n is equal to 2017? So we basically look like, and it doesn't matter, you might also need to justify why it doesn't matter the order of these people. But I think we're a little past that. So when n is 2017, we come in, we're looking at a 2017, 2 to the 2017 minus 2017, so 2 to the 0. Two to the 0, and then a 2016 times 2 to the 1. So with step 1, now suddenly we round down. So now it actually matters. And what exactly is this number? What are these numbers? Because determine what justification the number of candies that each student has when the procedure ends. Okay, so I kind of need to know what A 2017 is. So I'll make the note, step 1 will actually do something, since A 2017, like all the AKs, is odd. Now, what is... I don't have a nice closed form for the A's, but remember my star, number of candies doesn't ever change. Never changes. So we started with 2 to the 2017 candies, and now that's got to be A to the 2017, A 2017, plus 2, A to the A 2016. But I know A 2016, or twice A 2016, is just A 2017. And here's where we have to be careful. Is it plus or minus? So A 2017 would be twice A 2016 minus -1 to the 2017. So that would be minus -1, so plus 1. So 2 times A 2016 will be A 2017 minus 1. So 2 to the 2017 plus 1 is equal to 3A to the 2017. Okay, so in theory this gets me my value for A 2017. But does it actually? Because I don't know what this number even remotely is. Yeah, I'm a little stuck as to what this is. Although I do know that the process sort of, I think, stops one or two things after this, if we remember our B part question. Okay, 3A 2017 is 2 to the 2017 plus 1. Does it really matter? I think the answer is going to be something like 2 to 2015. As I recall, I said something to that effect. Okay, well, what happens if I do 2 to the 3 plus 1? That's 9, and so that's 3 times 3. 2 to the 4 plus 1 is not a multiple of 3. 2 to the 5 plus 1 is not a multiple of 3. 2 to the 6 plus 1 is not a multiple of 3. A lot of these aren't multiples of 3. 2 to the 7, however, is. 2 to the so 129 divided by 3. So that's 3 times 43. How does that relate to any of... I was hoping to find some sort of pattern or something. 2 to the 5, I completely skipped over 2 to the 5. 2 to the 5 plus 1 is 3 times 11. 2 to the 7 plus 1 is 3 times 43. Not seeing anything as a pattern here. I was really hoping that this would in some way be related to the numbers that we like. And I guess technically it is. We've seen 3, we've seen 11. 43 doesn't seem right. Oh yeah, no, 2 times 11 plus 21. Yeah, 43 was the next one. So yeah, this is actually making sense. But this doesn't help me figure out what exactly 2017 is. Oh well, we know it's odd. So let's go with that. Let's go with that. And actually, no. Number of candies doesn't change, so this is 2A 2017. No. Okay, so this guy is 2A 2016 minus -1 to the, so plus 1. 2A 2016 plus 1, and then A 2016 times 2, which, so that's what these numbers actually are, and then after step 1, we get 2A 2016, 2A 2016, 2A A 2016. And after step 2, it's still going to be A, because they already have the same number here. Okay, so eventually they all have twice A 2016 candies. However, that doesn't really make sense to me, because, I mean, what did they have before? Back in question number, in B, it was not that simple. So B, we start with 16, that's 2 to the 4. 1 round, down to 2 to the 3s. 2 rounds down to 2 to the 2s. 3 rounds, that's 2 to the 2, and 3 times 2 to the 1. After another round, we get 2 times 2 to the 1, and then 5 times 2 to the 0s. Those dropped by 1 and became 4. But there, for this one here, this is so 5 is A to the 4. So this is A4 minus 1, but that's not 2A3. Right? Because A4 is 2A3 minus negative 1 to the 4. So that'd be minus 1. So I would need plus 1 to get this. So there's the problem. Okay, that's why this doesn't... Because I was wondering, in this stuff, in B part, we didn't immediately get the same number everywhere here, but that's because we started with 2 to an even number, not 2 to an odd number like we have here in question D. Alright, that was bugging me. Yeah, so eventually I'll have 2 times A 2016 candies. How many candies is that? Well, number of candies was constant until step 1 was applied from an earlier observation. So that told me 2 to the 2017 was, we won't use, well, yeah, we will, we'll say A 2017 plus A 2017 plus 2A 2016. This I know is true. But now this is 2A 2016 plus 1 plus 2A 2016 plus 1 plus 2A 2016. So that's 6A 2016 plus 2. So 2A 2016 is 2 to the 2017 minus 2 all over 3, and that is the number of candies they have left. That took a while. That was a lot longer than question 4 on the Friar probably should be. So I'm wondering how much justification. I mean, it's at most like a 4-mark question. So what would they have needed justification for? Step 1 doesn't occur until like the very end. Probably talking about that sequence of odds, and maybe the justification for that pattern repeating. Or at least noticing that pattern repeats, and then the final answer. Maybe, I don't know. That seemed like a lot there. Maybe I just wasn't going through the question the right way. But I did get the answer, or what I think is the answer. I don't have the solutions in front of me because I try and do this natural. But yeah, 2 to the 2017 minus 2 over 3. Yeah. And that's the number of candies. Okay, so that finishes off the 2017 Friar. For more written contests from 2017, the Galois will be coming up. Of course, the Hypatia for grade 11, and the big one, the Euclid paper. If you're looking for a lot of written questions, there's 10 of those on the 2017 Euclid. However, you don't have to watch the Galois next or anything like that. Take a look at any of my contests, my contest videos. Whatever you're practicing for, try and find a video that matches that. Okay? And either way, I will see you guys for more math in the future. Thanks for watching.